Welcome to qnawire.
What we have is 1.930 that we prepared in 25 milliliters of a solution, and we are given the information of the pKa. We are also told that to neutralize that, we required a certain volume of 0.112 molar of HCl. So first of all, let's consider the neutralization reaction of that sodium salt producing Ha, that is the conjugate acid, and you're going to realize that we're going to have a one-to-one relationship in between HCl and the sodium salt. Thus, the amount of mole of HCl that we added at the equivalence point, it is going to be equal to the amount of mole of the sodium salt that we had. Doing the calculation, taking into account the conversion factor for milliliters to liters, we find that the amount of mole is 3.2704 times 10 to the minus 3, or 3.27 times 10 to the minus 3. Now, for the first part, in order to know the molar mass, we simply need to divide the mass that we added divided by the amount of mole that represents. And with that, we find the molecular mass or molecular weight of 591 grams per mole. Next up, for part B, we are going to add 10 milliliters of HCl. Those 10 milliliters correspond to adding an amount of H plus to our solution of 1.12 times 10 to the minus 3. So we're going to do our ice table in moles directly, taking the initial amount of A minus that we have and the amount of H plus that we added. Here we need to realize that H plus is going to be our limiting reagent for our reaction. Thus, all of the H plus that we added is going to react in order to give us the final concentrations of HA and of A minus. Sorry, the final amount of mole. So now, with this final amount of mole, we can calculate the concentrations of A minus, which is going to be 2.15 times 10 to the minus 3 divided by the total volume that we had. We begin we began with 25 milliliters and we added 10 more milliliters for part B. So we have 35 times 10 to the minus 3 liters. The concentration for A minus is going to be 6.14 times 10 to the minus 2 molar. Now, for HA, the result is doing the same procedure and divided by final volume, and we end up with 0.032, which is 3.2 times 10 to the minus 2 molar. Perfect. So far we have found those concentrations, but we still need to find what is going to be the value for H3O plus in order to get the pH of the solution for part B. Thus, the next step is considering the hydrolysis reaction that we have. And for this, the values that we are going to employ is initially HA is going to be 3.2 times 10 to the minus 2. The water is a pure compound, so it doesn't matter. H2O plus is going to start at 0, and A minus will be 6.14 times 10 to the minus 2. Now this ice table, it is going to be in molar concentration because our target is going to be the value for H3O plus. Next up, we're going to have the amount of change that we're going to call it x. We're going to have a diminish in x. Here we're going to add x, and we're also going to add x on this side. And at equilibrium, we're going to have 3.2 times 10 to the minus 2 minus x x and 6.14 times 10 to the minus 2 plus x. Nice. So now, using this, we can find, using the acidity constant, that let's recall the definition was concentration of H2O plus times the concentration of A minus divided by the concentration of HA. This turns into x times 6.14 times 10 to the minus 2 plus x divided by 3.2 times 10 to the minus 2 minus x. So now we only need to find the value for Ka, but since we are given the pKa for our reaction, that is 4.55, that means that Ka will be 10 to the minus 4.55. Thus our equation becomes 10 to the minus 4.55. And here we have two options. One is keeping all of the values that we have here, and the other one is solving the associated quadratic equation that you can find by just following the algebra, or by putting that expression into Wolfram Alpha or a similar computer software that you want to use. Or you can also expand and try to solve it by the general formula. Minus x. But since we know that the values for x is going to be is much smaller than the concentrations that we are considering. So if x is much smaller than 10 to the minus 2, we can make the approximation that on this side we can disregard the x, and on this subtraction we can disregard the x as well. Okay? So if we employ that approximation, that we can later verify that it is going to be true, the equation becomes 6.14 times 10 to the minus 2 x divided by 3.2 times 10 to the minus 2. Thus, x will be equal to 10 to the minus 4.55 times 3.2 times 10 to the minus 2. All of this divided by 6.14 times 10 to the minus 2. By solving this, using the approximation that I mentioned, we find a result of 1.47 times 10 to the minus 5. So it seems that our approximation is a good approximation, and let's recall that this is going to be equal to the concentration of H3O plus that we had. Now, if you want to solve the quadratic expression, the result that you find is exactly the same. Actually, if we solve the full quadratic expression, the result of x is 1.467 times 10 to the minus 5 molar. Okay? So, since in both of the cases we are going to approximate to two decimal points, it doesn't matter, and our final result for the concentration of H2O plus is this. Now, to find the pH, this will become minus logarithm of that concentration, which is 4.83. Nice. So now for the final part, what we are going to do is we're asked what is going to be the pH of the solution at the equivalence point. So what is going to happen at the equivalence point is that we are going to start with our salt, NaA, A. Actually, I'm going to write down directly as the ionic equation. A minus plus H2O plus coming from the acid is going to generate HA plus H2O, right? So at the initial point, we said that we had 3.27 times 10 to the minus 3 mole, but in this case, it really doesn't matter that much. We're going to see why. So that means that we need to add the same amount of acid. The change, it is going to be that concentration. I'm going to call it C0. We're going to produce C0 of HA. And at the equilibrium, we're going to get, in this case, something close to zero in both of the cases. And we find a C0 concentration of HA. Now, what I'm going to do is erase a little bit here just to have more space. End it up without. So the concentration of HA, it is going to be the amount of mole of HA that we have, which is 3.27 times 10 to the minus 3, divided by the final volume that we have. The amount of volume, we are told that we started with 25 milliliters plus the amount of HCl to achieve the equivalence point, that is 29.2, and of course multiplying this by times 10 to the minus 3. With this, our concentration of HA at the equivalence point before we consider any dissociation is 0.06 molar. Okay? So now the reaction that we're going to consider, now I'm going to erase this part because I'm out of space in this page. Now the next step is considering again the hydrolysis reaction. In this case, we're producing HA in aqueous solution plus water, liquid, producing H3O plus A minus. Aqueous and aqueous in both of the cases. Again, we begin with our ice table. We know that our initial concentration, it is going to be 0.06, everything in molar concentration. Water doesn't matter. We start at 0. And the initial point of A minus, it is going to be something close to 0 because we assume that everything reacted at the equivalence point. So now the amount of change, it is going to be minus x. We're going to generate x and x of both of them. And at equilibrium, we have 0.06 minus x, x, and x. Thus, our equilibrium constant is going to, which is the same acidity constant that we employed in the last part, divided by HA, now turns into, first of all, 10 to the minus 4.55 equal to x and x, both of them multiplying, divided by 0.06 minus x. Now, we are going to make the same approximation as we did before. That means considering that 0.06 is much larger than x. So this equation becomes x squared divided by 0.06. With this, solving for x is the same as taking the square root of the Ka times 0.06, which give us which is going to give us 1.3 times 10 to the minus 3 molar. Again, this is the same concentration as H plus or H3O plus. Thus, our pH, that is minus the logarithm of that concentration, is going to be 2.88. Actually, 2.886, which is 2.89. I'm going to write down here 2.89. And those are the final answers for both of the problems.